Hello everyone, this video is the last video for the section of MyLab review. This question is about how to create a function file which can calculate cosine x based on Taylor series expansion. So the Taylor series expansion for cosine x is shown in this equation. The x here is in radians. And this question asks you to write a MyLab function file, which is called mycosine.m, that determines cosine x using this Taylor series expansion. The function file asks the user to type the input parameter x, which is an angle in degrees. And then it uses a loop for adding the terms of the Taylor series. If Sn is the summation of the first n terms, the estimated error can be calculated as epsilon, which is equal to the absolute value of Sn minus 1 over Sn minus 1. The stopping criteria for this is that we stop adding terms when epsilon is less than or equal to 0.000001. The output parameter result is the approximate value of cosine x. So the first line of this function file should be function, the output parameter result, equal to the name of this function file, mycosine, and the input parameter x. So let's start writing this file. We need to create a new script. Function result equal to mycosine, the input parameter x, and then we save it as mycosine.m. All right. So because in this question it asks you to stop adding terms when epsilon is less than a certain value, so it's better that we use a while loop, because when we use while loop, we can define our own stopping criteria very easily. So while epsilon, so because we stop adding term when epsilon is less than or equal to a certain value. So we continue this loop when epsilon is larger than this value, right? So it should be 0.000001. All right. Then when this condition is satisfied, we can continue adding terms. So assume each time we add a new term. So the new term should be in this Taylor series expansion. So as you can see, it's minus 1 to the power of n over 2n factorial, and then times x to the power of 2n, okay? So it's 1 negative 1 to the power of n over 2n factorial. We can use the built-in function factorial to calculate the factorial of 2n. And then this whole thing times x to the power of 2n, right? All right, so this will be the new term. And in the next iteration, we will get another new term. So when we calculate in the next iteration, we need to make this n equal to n plus 1, right? So then the new summation, assume its sum, should be equal to the summation from the last iteration plus this new term. So this will be the new summation. Then we can define the epsilon, so which should be the absolute value of Sn minus 1, which is the difference between the new summation and the old summation in the last iteration. So the difference is actually the new term, right? So over Sn minus 1. Right now the sum is already updated in this line. So if you want to get the old sum, so it should be the new sum minus the new term, right? So this will be the epsilon. So then we end the loop. In the end, the output parameter result should be equal to this sum. So we need to initialize those variables. First, you can see here, the x value in the Taylor series expansion is in radian, but the input parameter x, when the user input, it's assumed in degrees. So we need to first convert this degree into radian. So here, x should be equal to x times pi over 180. So we changed this from degree to radian, but there are a few other variables we need to initialize. So what's the initial value of sum? We can assume it's 0. And there are many different ways of doing it. You can assume initially the sum is 1, right? And when we add new term, n is 1, then we add this term. Or you can assume initially the sum is 0 and n is 0, so we add this 1. Okay, so it will be the same. So we assume sum is 1 and n is 1. Okay. All right, then we need to initialize this epsilon, because epsilon should be larger than this value so that we can go into this while loop, right? So the while loop will be triggered. If it's smaller than this value, then you never go inside the while loop, so you didn't do anything. So in order to make sure epsilon is a large value, we assume it's 100. Okay. All right, so let's save it. And let's call this function in the command window. So my cosine, for example, 45 degree, it gives you this value. So let's see the cosine, the built-in function in MATLAB, which is cosine. The input parameter should be in radian, so 45 should be pi over 4. Okay, so they are quite similar. Let's see, my cosine 81 and the cosine 81 times pi over 180. Okay, so I think this works. And think about this, and if you have difficulty understanding those examples, I suggest you to review MATLAB in the first week of this class. We don't need like fancy features like toolbox or symbolic in MATLAB in this class. So you just need to review the very basic knowledge, like how to do while loop, how to do for loop, how to do matrix operation, vector operation, how to create a function file, how to call this file in the command window or in the main file. That will be totally enough. You can have access to MATLAB through the virtual machine if you are on campus, or you can buy a student version of MATLAB, which is only $50. So MATLAB is really important for this class. So I suggest you to review the materials in your previous programming class, so that make sure you can understand the content of this class. At the end of this class, I will give you the first quiz. So remember that we have one quiz every class. So this quiz, you have 40 minutes to finish. You need to submit the MATLAB code for this function file, which is called bsum. So the B sum of y for the input parameter is x and the result is y. It's defined by this equation. All right. So the function file, the name is bsum. So bsum.m, the input parameter x and the output parameter is y. The first line is given to you. You just need to write down the content, like how to calculate y based on the input from the user. So assume you know x and n from the user, you need to give me the value of y. Okay, so at the end of the 40 minutes, you need to submit your code. Good luck. So next time we'll talk about the new material of this class, which is about finding the root of nonlinear and linear equations using a technique called bisection method.